So suppose you are manufacturing roller bearings. And so these are cylindrical, and they're supposed to have a diameter of 4 centimeters and a length of 6 centimeters. But there ain't nothing in this world is exact, right? So if you pick up a roller bearing coming off the conveyor belt at random, then let's take X to be the diameter of the one you've chosen. It's going to be normally distributed with mean 4, and suppose the standard deviation is 0.01 centimeters. And then its length is going to be normally distributed with mean 6, and we'll also suppose that the standard deviation there is 0.01 centimeters. Now, if you've got one machine that's rolling out the cylinder and another machine that's cutting off the lengths, then you probably expect that these are going to be independent random variables. Because what happens in one machine probably doesn't influence what happens in the other machine. So that means then that the joint PDF of this guy is going to be the product of the two of them. So it's going to be F1 for X and F2 for Y. And so if we look up in our table of probability distributions, what it looks like, we're going to have 1 over the standard deviation times the square root of 2 pi times e to the, and then we're going to have negative x minus the mean, which in this case is 4, divided by 2 times the square of the standard deviation. So it's going to be 0.0002. That's our F1. Our F2 looks very similar, except that the mean is now shifted over to 6. So this is e to the minus, and then we've got y minus 6 divided by the same standard deviation squared times 2. And so this is then, okay, so multiplying this out, we get some god-awful number. What is it? So it's 5,000 over pi e to the minus 5,000, and then we've got x minus 4 squared, y minus 6 squared. All right, so what's going on here graphically is that if we look at the distribution function, we're interested in where we've got, so here's, maybe that's mu1, and we want to see, we're looking at whether or not we're within some certain bound of that particular mean that way, and then we've got mu2 going the other way, and we've got some similar tolerance. So we actually want to check to see that we're in some little square right here centered at the mean of this distribution. And I'll try giving you what this looks like. This is going to suck. What's really going to suck if I start by mislabeling my axes. That's just tragic. Okay, so then we've got, okay, so here's, say, boom, there's mu1, and boom, there's mu2, and then so the this is where our Gaussian is centered, so it's doing some thing that looks like that, and something that looks like, something that looks like that. And if I were to draw some like level curves in place here, they'd be, oh wow, that's really bad. Okay, and then so I'm looking at what the probability is that's in some little zone like this, centered around the middle, something like that. Okay, that gives you the general idea. So let's consider, like, how likely is that either one of these measurements is more than 0.02 from the mean. Okay, so what I want to find is what is the probability that the distance between x and the mean is bigger than 0.02, or the distance between y and its mean is bigger than 0.02. So what's the probability that either one of those happens? Well, we can use this handy property of probability that tells you, okay, so the probability that x takes the value in a, this is a different x here, you know what, let's call this something else. The probability that a random variable takes its value in a plus the probability in that it's not in a, that has to equal 1, because we're summing up all possible things, right? All possible events are it happens or it doesn't happen, right? So that's like a disjoint union of possibilities. And that means that we can write the probability that something happens as 1 minus the probability that it doesn't happen. Okay, so and it turns out that this one here is easier to compute in terms of we can just set it up as a single integral. So we'll do that. So we're going to look at the probability now. So now we have to figure out, okay, so what is like the opposite of neither, so either this doesn't happen or that doesn't happen. Well, that would be the same thing as if this one is close to its mean and this one is close to its mean. So the probability, it then becomes x minus mu1 less than or equal to 0.02, and because we're negating it, the probability that y is within 0.02 of its mean. Okay, and so that's putting us in the purple box right here. Okay, so that's the integral that we have to compute. So let's see. So this is going to be, so now we've got x is going to be, let me just write a little scribble here on the side. So this is the same thing as 3.98 less than or equal to x less than or equal to 4.02. Right, that's the interval that x can be in order for it to be within 0.02 of its mean. And for y to be within 0.02 of its mean, it can go down to 5.98 and up to 6.02. And so those are going to be the bounds of our integral. So there's the x bounds, and then the y bounds are from 5.98 up to 6.02. And then we've got our hideous joint PDF, so 5,000 over pi. I say hideous, but really it's a thing of beauty. It has so many neat properties and describes so many things and can be used in so many different ways. So let me just, all right, write that up there. Okay, that was dy dx. And then by the magic of independence, we can write this 3.98 4.02 e to the minus 5,000 x minus 4 squared dx times the integral from 5.98 to 6.02 e to the negative 5,000 y minus 6 squared dy. It turns out that e to the minus t squared, there's no elementary antiderivative for this. So you can't do it analytically. You have to resort to something numerical. So at this point, you ask a computer, or you look it up in a table of values. The normal distribution has, there's like tables of values for these kind of things. But nowadays, just use a darn computer, right? That's what computers are there for. And we find out that this is going to be about 0.91. Okay. So the probability that either dimension is off by where by off I mean differs from its mean by more than 0.02 is going to be 1 minus 0.91, which is 0.09. So in other words, you've got like a 9% chance that one of the dimensions is going to be real bad.